Hello, my name is Mikhail Nestorenko. I am presenting the joint work with Joseph Oglio, Kendrick Hood, and Gokarna Sharma. We're all out of Kent State. Our work is titled Byzantine Geoconsensus. I'm the last author, so they told me to make myself useful, so I'm doing the presentation. The outline is this. First, I introduce the problem of consensus and geoconsensus. I discuss the impossibility of geoconsensus in a particular setup. Then I'm introducing the basic solution, and that this basic solution requires that certain nodes to be placed in a certain predefined distance away from each other. Then we develop a generic solution that lifts this restriction. Let me talk about the classic consensus first. The setup was this. There is a synchronous reliable communication and the network is fully connected. The algorithm is deterministic and the faults are Byzantine, meaning that a faulty process can behave arbitrarily. The consensus is binary. Each process at the beginning of the computation is input 0 or 1, and each correct process decides and outputs either 0 or 1. These decisions are subject to the three classic properties: agreement, validity, and termination. Let me now introduce the problem that we defined, the geoconsensus. Each process has unique 3D coordinates. That is, the processes are embedded in a two-dimensional plane. If the fault can affect any process on the plane, then the problem is no different than the classic Byzantine consensus and no more new results can be obtained. So our idea is to restrict the fault location. And the restriction is as follows. The fault area is a finite-sized convex area where each process inside that area may be faulty. The adversary is allowed to place the fault area anywhere on a plane, and there may potentially be multiple areas that the adversary can control. Correct processes, on the other hand, know the fault area shape and size, but not the location where the area is to be placed. And the geoconsensus is for the correct processes to arrive at consensus despite these faults. Let's address impossibility first. A coverage number is the minimum number of areas required to cover each process in the network. For example, in this network, the coverage number is 3 because all the processes could be covered in 3 sets. Theorem 1 says that given a set of processes, the geoconsensus is impossible if the coverage number is less than 4. The intuition is pretty straightforward. If the coverage number is 3 or less, then like here, then say processes in set C will not be able to determine if the faulty processes are in set A or in set B, and therefore may not arrive at the same solution as the correct processes in the other set. So this is right. So let's talk about the solutions. So the first algorithm that solves the geoconsensus problem we call basic. We borrow a classic Byzantine consensus algorithm stated by P. Shostak and Lamport. We could use other algorithms, but this is the most widely known. So basic operates as follows. If there are 9m plus 3 processes, m is the number of faulty areas. With a pairwise distance between them greater than the diameter of the fault area, like so, then the algorithm works as follows. Each process selects leaders mutually removed further than D using some deterministic greedy heuristic. Leaders then run PSL and broadcast their decision. All processes adopt leaders' decisions. Intuitively, the greedy heuristic is guaranteed to find at least 1/3 of processes that are further than distance d away. And the PSL solves classic consensus if the number of faults is less than 3m. Therefore, we'll need this many processes for the solution to exist. Now the question is, can we do better? Do we really need this restriction? We'll have to develop a solution towards that, lifting the restriction. Let me now describe the generic solution. First, we study the coverage of the processes in the network by fixed size squares. We define a square cover problem, determine it to be NP hard, then develop a two approximation heuristic of the optimal solution. Use it to describe the generic algorithm. We study the bounds or requirements for the coverage that when the network is covered by squares and the fault areas are also squares. Then we extend it to circles and to the higher dimensions. So the square cover problem. So suppose processes are embedded in a 2D plane such that the coordinates of each process are unique. The square cover problem is to determine if a certain number of square areas A can completely cover these processes. It turns out that the square cover is NP hard or NP complete, and the proof is by reduction to box cover. In the paper, we present a heuristic G, we call G square, that provides a two approximation of the optimal solution. Let me discuss the heuristic. We enclose the processes of the network in the smallest possible rectangle. Then, starting from the bottom, we cover the processes in so-called slabs. A slab whose height is the same as the side of the squares we are covering the processes with. Well, the first one is at the bottom of the rectangle, and the next one is placed such that its bottom side touches the first process outside of the previous slab. And we continue this way upwards until we fill the whole rectangle with slabs. Inside the slab, we place the squares as follows. The first square is placed such that its leftmost side is touches the process, the first process. The next one is placed such that its leftmost side touches the process that's not covered by the previous square, and so on. So that's our placement of squares. We claim that G square provides a two approximation of the optimal solution on the number of squares. The intuition is this. We prove that the placement of squares in a slab is optimal, meaning that there could not be another way of placing the squares inside the slab that covers all the processes inside the slab. We also show that an optimal solution could cover processes in at most two slabs, hence two approximation. The generic algorithm is relatively straightforward. Each process independently computes the set of covers, G square. Then each process deterministically selects leaders for each a leader for each cover. The selected leaders run PSL, and after arriving at a decision, broadcast their decision to all other processes. The remaining processes adopt the reached decision. Let me give you an intuition as to how we arrived at the number of squares in the coverage area A for a particular number of fault areas. Lemma 9 says in part that if that area, fault area F, regardless of orientation, may overlap no more than 7 squares of the coverage area A. Indeed, 1, 2, 3, 4, 5, 6, 7. Theorem 5 says in part that given a set of processes N and a single fault area F, the coverage area A of generic can tolerate up to n-15 faults provided that the number of squares in the coverage area is greater than 22. Notice, by the way, almost all processes in the network may be faulty. Why is that so? Well, the fault area F may potentially provide faulty leaders for up to 7 coverage areas here. However, PSL would still work correctly provided that more than 2/3 of the processes are correct. So the number of correct leaders need to be 2 by 7 plus 1, which is 15. Now let us talk about coverage areas. We have 22. So 2/3 of those is 2 by 22 and divided by 3, which would be 14.6 plus 1, which is 15 plus 15.6, which is greater than 15. So that's why the theorem 5 holds. Here is the full theorem 5. So the portion I just described is the first bullet. And however, if the single fault area is axis aligned, then generic may tolerate even greater number of faults with fewer squares in the coverage area. And if the fault area is somewhat smaller, then again, greater number of faults with fewer squares in the coverage area. Theorem 6 extends this result to the arbitrary number of fault areas greater than 1, and the numbers are similar except they're multiplied by the number of fault areas. We extend our results to circles, both a circular fault area and circular coverage. So the idea is this: a circular fault area could potentially cover up to 1, 2, 3, 4, 5, 6, 7, 8 squares. And we also circumscribe a circle over a coverage square, and we could use the techniques of squares with the circles. That gives us theorem 7, where if the fault areas and covered areas are circles of the same diameter, then we can tolerate this many faults with a number of fault areas, fault circles, being at least 1 and potentially greater, provided that the number of circular coverage areas are this much. Now, if the circular fault area is large, number of faults is stated as such, and the number of circular coverage areas are those. Similar, if it's smaller, then the numbers are as follows. We extended our results to dimensions greater than 2. Specifically, we worked on a 3D case and manipulated cubes and spheres. And that yielded theorem 8, where we applied techniques similar to the 2D case, and we got results where fault area was a cube and the cover set were also cubed. The fault area was not axis aligned. We got these bounds. Now, if fault area was an axis aligned cube, then the bounds are these. If fault area was a sphere and so was the cover set, then these are the bounds. There is no particular reason why these techniques couldn't be applied to a higher dimension case. To review, we posed an original geoconsensus problem, proved it impossible if the set of processes can be covered by less than 4 areas the size of the fault area, presented a basic solution required the set distance between some processes, lifted this requirement and developed generic algorithm that solves geoconsensus problem. For that, we studied how processes can be covered by individual areas, showed that the coverage is NP hard, but provided an efficient heuristic. Then we determined coverage requirements using this heuristic for the case the fault areas are square, circular, or 3D. This concludes my talk. Now, are there any questions?